Hello everyone, thank you for joining today. My presentation will focus on two state-of-art unsupervised neural methods for combinatorial optimization. These approaches propose new methods of learning heuristics and solvers for NP-hard problems without any supervision or reinforcement singular. We will go through two groundbreaking papers, the UTSP which tackles TSP using graph neural networks, and the DIFF-UCO, which introduces diffusion models for general combinatorial optimization problems. Let's start by understanding the motivation behind these efforts. At first, we will introduce the unsupervised learning for solving the traveling salesman problem, which is published in New Rips 2023. This work introduces a novel method which is called UTSP, and this framework uses unsupervised learning with graph neural networks to solve TSP instances without requiring neighbor data or reinforcement learning signals. To ground this discussion, let's briefly recall the traveling salesman problem. Given a set of cities and pairwise distances, the goal is to find the shortest route, and this route can exactly visit each city once and finally returns to the start city. This problem is a well-known NP-hard problem, which means the exact solution scales poorly with the number of cities increasing. Traditional solvers such as Cockroach are powerful but computationally intensive. Heuristic methods such as LKH are fast but handcrafted. More recently, machine learning approaches have emerged. However, supervised learning requires costly optimal tools as labels, and reinforcement learning suffers from sparse rewards and instability. This motivates a new approach, unsupervised learning with inductive biases for the traveling salesman problem. The UTSP framework operates in two main stages. First, a graph neural network predicts a soft indicator matrix, which represents the likelihood of each edge being in the tour. This is converted into a heat map. Second, a local search algorithm uses this heat map to guide the construction of a valid TSP tour. The key here is that the entire graph neural network is trained in an unsupervised way, using a specially designed surrogate loss function that enforces both path length minimization and the Hamiltonian cycle constraint. We can see that this figure gives us an overview of the pipeline proposed in this paper. On the left, we can see that the cities is inputted as coordinates, and these coordinates go into the graph neural network, which outputs the software indicator matrix T here. Here it is T. Without transformation, the indicator matrix T can result in invalid paths, like the route with loops shown in the middle. We can see that this is the route with cycles, which is invalid tour. To fix this, a transformation is applied to convert the indicator matrix T into a proper heat map. That is this transformation T to the H transformation, which is shown in here. And this transformation can better approximate a valid TSP tool. And this is the overview of the UTSP proposed in this paper. Now let's dive into the neural architecture. The orders use a graph network variant, which is called SAG. That is the scattering attention graph neural network. This is a crucial part of the model success. Typical graph convolutional neural networks suffer from something called oversmoothing, where load features become too similar as information is aggregated across layers. This oversmoothing makes it hard to distinguish between good and bad edges. The scattering attention graph networks addresses this by using both null pass and band pass filters. Low pass filters capture general structure, while band pass filters highlight local variations. This combination allows the model to retain sharper distinctions between node relationships. The output of the graph network is a matrix where each entry represents how likely it is that one city follows another in the tour. This isn't a tour yet, just a probabilistic blueprint, but it sets the stage. It sets the stage for the next step, turning it into a structured guide. So we have a soft matrix from the graph network, but it doesn't necessarily form a valid tour. The matrix might suggest multiple outgoing stage edges from a city, or even loops, which we don't want in a TSP tour. To address this, the authors introduce a transformation that converts the soft matrix into a heat map. This heat map is designed to look like a Hamiltonian cycle, a path that visits every city exactly once and returns to the start. The transformation is carefully constructed to preserve differentiability. Differentiability. That means we can still backpropagate through it during training, even though it creates something that looks more like a complete tour. This step is a key innovation. It bridges the gap between raw neural outputs and structured combinatorial solutions, all while staying compatible with gradient-based learning. Since we don't have labels or rewards, we need a different way to train the neural network. The authors solve this by designing a surrogate nodes, a set of penalties that encourage the network to behave as if it is learning the TSP. There are three main components. First, it pushes the model to select only outgoing edge per city, ensuring each node is visited just once. Second, it penalizes self-loops. Cities that collect back to themselves will be penalized. Third, It minimizes the total expected tour length, which is calculated using the distance matrix and the heat map. What's important is that all these parts are differentiable, so they can be used in gradient descent. This allows the model to learn from scratch from nothing but graph structure without needing any external supervision. We can see from this formulation, there are three parts, and each part will give a constraint and give an objective for this for our training. Once the model is trained, we can use it to solve new TSP instances. But instead of taking the soft heat map and directly converting it into a tool, which can be difficult and unstable, the authors use it as a guide. They apply a local search algorithm based on k-opt moves, which are common in traditional TSP solvers. The key difference here is that instead of searching blindly, the algorithm uses the heat map to prioritize which edges to explore or modify. It's a kind of best first search and guided by the edge probabilities in heat map. But it also includes a randomness term to encourage exploration. This balance between following the model's suggestions and exploring new paths allows the method to find high-quality solutions efficiently. The model is trained on graphs ranging from 20 to 1,000 cities. For evaluation, it's compared to exact solvers such as concrete, as well as learning-based baselines, including reinforcement learning. And supervised pointer networks. One of the most impressive aspects is that UTSP uses less than 0.2% of the training data used by reinforcement learning or supervised learning methods, and about 10% of the parameters, but still performs competitive. This shows the power of the inductive bias and the quality of the heat map-based local search. The performance results are summarized in these tables. On small graphs, UTSP, we can say that on small graphs, UTSP matches the optimal solution produced by concrete. On larger graphs, where concrete and learning-based baselines start to struggle, UTSP continues to perform well. What stands out is the gap between UTSP and other learning methods on large problems. For instance, some reinforcement learning models deviate by over 20 or 30% from optimal, while UTSP stays within a few percent. This shows that inductive bias and search strategies are very effective, especially when scaling to harder problems. The authors also perform a comparative analysis of different graph neural architectures. They look at the graph convolutional neural network, the standard graph, and compare it to SAG, the model they use, that is the scattering attention graph neural network. They find that graph convolutional neural network tends to oversmooth the graph and produce uniform heat maps. We can see that from the left part of this figure, which are not helpful for and such uniform heat maps are not helpful for guiding search. However, the scattering attention graph-related work produces much sharper distinctions, and it highlights which edges are actually more important. They visualize the heat map to show this difference, and also track training nodes to confirm that scattering attention graph-related work leads to better optimization. This reinforces the point that architectural choice matters, especially in unsupervised combinatorial learning. One more benefit of the heat map is that it enables aggressive pruning of the search space. Normally, a complete TSP graph has thousands of edges, especially as the number of cities grows. Evaluating all of them would be expensive, but with the heat map, we can restrict the search to just a few hundred high-confidence edges. For example, on a 100-node graph, the method retains only about 10% of the total edges, but it still captures almost all the correct edges from the optimal tool. This makes the local search phase much faster without sacrificing solution quality. It's another example of how learning structure, even in a soft form, can dramatically improve efficiency. In summary, this paper presents an outstanding unsupervised method for solving TSP using graph networks. It combines theoretical insights with practical efficiency. These surrogate nodes encourage short loop-free paths. The transformation from T to H approximates a cycle structure, and the heat map guides a stochastic local search. Despite using no labels and minimal data, UTSP performs at or above the level of prior learning-based methods, especially on large graphs. It's a promising direction for real combinatorial optimization. Then we will move to the next paper, which is titled A Diffusion Model Framework for Unsupervised Neural Combinatorial Optimization. And this paper is published in ICML 2024. This work proposes a new method to solve combinatorial optimization problems using diffusion models without needing any labeled training data. Combinatorial optimization involves finding an optimal configuration from a discrete solution space. We can represent many combinatorial optimization problems with an energy function, Hx, which assigns a cost to each binary solution, x. Instead of searching directly for the minimum, we can reframe this as a probabilistic sampling problem. The ideal is to sample from Boltzmann distribution, where low energy solutions have higher probability. As the temperature T approaches zero or equivalently, beta approaches infinite. The distribution concentrates its mass on optimal solution. However, this distribution is generally intractable due to the exponential size of the solution space. Many modern generative models aim to learn the Boltzmann distribution. A natural training objective for this is minimizing the reverse KL divergence between the model distribution Q theta x and the true distribution PB x. This results in a loss that combines the expected energy and the entropy of the model. Unfortunately, evaluating log Q theta x is impossible for latent variable models such as diffusion models and variational autoencoders, since they require integrating over all possible latent variables. That's where this paper contributes. They develop a workaround that enables the use of expressive models despite this issue. Instead of trying to minimize the intractable KL divergence directly, the authors use a tractable upper bound. They show that by considering the joint distribution over the solution and the latent variable, we call this latent variable as Z. We can bound the original KL divergence by a joint KL divergence over X and Z. This upper bound still pushes the model towards the target distribution, but avoids the need to evaluate marginal likelihoods. This trick is key to enabling diffusion models in this domain. The figure visualizes the entire generation process, the forward diffusion process, as noise iterative to an initial value solution, eventually reaching a lower distribution like uniform noise. The model then learns the reverse process, taking a noise vector and deploying it step by step to recover a value no energy configuration. The beauty of this approach is that we don't need supervised labels for valid or optimal solution. Instead, the structure of the diffusion and the loss implicitly guide the model to find better configurations. This loss function is central to the approach. The first term prompts exploration early in training by encouraging high entropy in the deloising steps. The second term ensures that the reverse process resembles the forward noise process. This is like consistency regularization. The third term incorporates the actual optimization objective, that is, minimizing the energy of the final deloys output. By combining these terms, the model learns to gradually transform noise into valid high-quality solutions. Two types of noise distribution are considered for the forward process. The categorical noise flips bits randomly, while any other noise is more intelligent. It considers the energy landscapes and uses a scaled Boltzmann distribution to bias noise towards low energy areas. Importantly, the paper shows that any other variant leads to more stable and effective training, especially when no temperature annealing is used. Once the model generates a sample, we can improve it using conditional expectation or this process iterative fixed variable values by checking which setting leads to a better energy score. It's greedy but very effective. Moreover, the authors introduce a variation called subgraph tokenization Instead of changing one variable at a time, we group key variables and optimize them together, which speeds up the process significantly while maintaining solution quality. The model is tested on 5 standard combinatorial optimization programs: the MS, Maxio, MDS, Mascot, and MVC. They use synthetic graphs from the RB model, which is known to be hard for solvers, and the variables Albert model, which generates scale-free graphs. The method is compared against strong baselines, including Groby, heuristics like mean field annealing, and other learning-based models such as LIFT and AGN. This variety allows for a comprehensive evaluation of the approach's strengths and limitations. We can see from this table, for different problems and the orders use different objective for the energy function. That is, the table with the energy functions of these 5 problems. And now we can see the results. On the MIS and MDS task, we see very strong results. For MIS, diffusion with conditional exploitation and with CE and SD gives the best performance on the large RB graphs. For MDS, even the plain leaf UCL outperforms previous learning methods and is close to the optimal solvers. This suggests the model effectively learns to prioritize better configuration even without labels, and CE refinement helps to close the final gap to optimality on Maxio and Mascot. The results are similarly strong. Particularly noteworthy is that on BA large graphs, diffusion surpasses Groby when the latter is time limited. This demonstrates that the practical potential of the method. We can get near optimal solutions in seconds using a GPU, which is often much faster than what traditional OR solvers can do on a CPU. We can see that the diffusion is much faster than the above algorithms. The ablation studies are very informative. Increasing the number of diffusion steps during training improves accuracy, but also adds computation. Interestingly, more inference steps, that is, delousing iteration, can further improve results even beyond the number of used during training. Also, we see that the annual noise distribution yields more stable training compared to the category noise. Finally, the CEST drastically reduces inference time while keeping the solution high quality. We can see that from figure 2. To summarize, this paper introduces an important framework that let us use diffusion models in unsupervised combinatorial optimization. By leveraging a clever upper bound loss, they sidestep intractable likelihood evaluation. Their method outperforms both heuristics and learning-based baselines across a range of combinatorial problems. Additionally, the tricks such as CE and tokenization make the approach scalable and practical. When I say that, if we see from the CE, how important the conditional expectation is. This the y-axis represents the solution quality, and the x-axis represents the evaluation diffusion steps. When I say that, with more diffusion steps, and the time will increase, and the quality of the solution will also increase. But if we use CE, the quality will improve more impressive. So it's a significant step toward using generative models for optimization tasks without labeled data. In a word, today we introduced two important papers for neural solvers for combinatorial optimization, that is using unsupervised learning to solve such problems, which is very novel, which is very important direction for this domain, in this domain. That's all. Thank you.